Hello, Jeremy here from Sadness Monday, and welcome to the BetterPhysics Speed Limits tutorial. Maybe you saw the showcase video, but today I will be showing you how to use the speed limits feature of BetterPhysics. This feature lets you write dead simple code and get awesome physically realistic movement that still has limits. So to start with, I have this super simple scene here. I've got a spaceship. It has a rigid body. It is constrained to the XZ plane. The Y position is constrained. It also is constrained to rotate only on the Y axis. And this thing has a very simple script, which I'll show you now. It literally just is handling some input to get thrust and yaw values. And then it's just add relative force in the forward direction, so whichever way the ship is facing. And this is a built-in Unity rigid body function. And then to rotate, we're just going to rotate on the local y-axis according to the buttons I press. So just a simple add relative torque. And let's see what this looks like. This is a pretty typical setup. So I can rotate, I can hit spacebar and thrust my way around. Now, the problem is I can go as fast as I want, which is great, and it feels nice, but most games want to have some kind of limit. And we have nice, realistic physical interactions with these spinning obstacles. They send us flying, and that is great, but most games want some kind of limit on the speed. So one thing that a lot of people will do is they'll open up their code, they'll go to fixed update, and they'll do something like this: rb.velocity equals vector3.clamp magnitude. And let's say we'll clamp that to 50. So this should give us a speed limit of 50, right? So let's see what happens when we do that. Let's run the game. Okay, we have a limit now. It doesn't seem to be properly clamping it to 50 for some reason, and I'll get into why that is in a minute. And also, when we get hit by this thing, it's not sending us flying like we want, so that's like not nearly as fun. In fact, that's very annoying. So there's a few limitations to this, and what a lot of people end up doing is some kind of complicated system involving coroutines, perhaps, that maybe disable the clamping of the velocity when you get hit by an external object. They might disable the script that moves the character for a little bit after you get hit by an object. And you end up with a lot of complexity, a lot of ugly code, a lot of code that's hard to understand and hard to maintain. And then as you add more complex interactions to your game, you have to fight with yourself often. So that's not ideal. So let's look at what you can do with BetterPhysics. So let's delete that ugly clamp line. And in fact, let's leave our code exactly as it is. We actually don't need to really touch the code at all here. What we are going to do is look at the inspector, and there's a better rigid body component on here. And you can add one of those very simply just by adding a better rigid body as a component, like any other component. I've already got one here, so I'm not going to add another one. So I'm just going to add a limit here. Just press the plus button, and I'm going to add a soft limit, and I'll explain what soft limits are versus hard limits in a little bit. And let's set that to 50. And that's an omnidirectional limit, and let's see what happens. So I can rotate, and now I'm holding the spacebar, thrusting, and I'm at exactly 50. I'm not at like 52. And by the way, the reason that we were going to a little higher than 50 before is that when we had that clamp magnitude code in fixed update, the way Unity works is when you call add force, that force doesn't actually get added until after all of your code is running. It actually gets added during the physics simulation itself. And so when we clamped our magnitude, that wasn't, our force still got added after the magnitude was clamped. So here, with BetterPhysics, just by adding this limit, we're clamped to 50 beautifully, perfectly 50. And now what happens when we hit this obstacle? We still get sent realistically flying, careening out into space, and we can take control as soon as we want just by hitting space again. And let's just see that again. Let's get hit by this spinny thing. Let's let us hit it in the back. Let's let it hit us in the back. So now we're moving 82, and if I hit space here, I can't go any faster by holding my thrust. But if I turn around and hit space, I can get right back up to my limit and slow down from that higher than the limit speed. So without adding any additional code, our code is still dead simple. It's still just add relative force. We now have this really cool interaction where we can freely control the character still after it gets hit by external objects and keep our limits. So this is already amazing, and you can do a lot with this. But wait, there's more. So there's other types of limits. We could do a world axis limit. Let's set a z-axis limit of, let's do 50 again. Let's see how that goes. And actually, I don't even need to stop and start the game to apply these limits. So you can see my speed is going higher than 50, but if we look at world space velocity here, the z-axis never goes over 50. I can move in any direction I want, except that if I go in the world space direction of z, I can't get higher than 50. Now, what happens when we get hit by an external object? We can get higher than 50. We go up to 212 here, and of course I can apply thrust as I need, and I can go as fast as I want on the x-axis. See, I'm going 100, 200, but my z never goes over 50. So this is great, and actually I can change this on the fly. Let's say I can change it to 25. Now we're stuck at 25. And x is still unconstrained. I can add an x limit as well. Let's add an x limit of 50 as well. Now we look at the world axis. We can go 25 on the z, 50 on the x, and we can freely control ourselves, and we can still be hit by external forces. So let's see what other kind of limits we can apply here. Let's just stop the game. Let's do a local axis z limit of 50. So now if we look at the local space velocity, we're limited to 50. You know, in world space we're doing this diagonal thing, but we can limit ourselves on the local z-axis. Now another thing you can do is you can mix and match. So let's say we do a world axis limit of, we could do 50 on the z-axis, and we can add also an omnidirectional axis limit to 100 in any direction. And let's see what that does for us. So we can reach this limit of 50 on the world space z-axis, but now we can go diagonal, and we can only get to about 50 on the z-axis in the world, but we can go 100 sideways or diagonal in terms of absolute speed. But then if we try to sort of do that in the z direction, we're limited to 50 completely on the z-axis in the world space. But if we go diagonal a bit, we get this, you know, it's giving us this weird diagonal movement, but that's a you know, a side effect of limiting ourselves this weird way. But the point is, you can do these sort of mix and match combinations, and the system will just take care of it for you. So the next thing I'd like to talk about quickly is the other type of limit, and that is the hard limit. And let's do a hard limit of 50. And this is going to behave a lot like the clamp magnitude approach, except of course we get our actual 50 meters per second limit instead of that getting a little above that. And if we hit an obstacle, we still get clamped to 50. And so this is sometimes useful for certain things. But the really cool thing we can do is we could have a hard limit of, say, 500, and we could have, actually, let's do a hard limit of 200 or 100, and we'll do a soft limit of 50. And so now we can move around at 50 with our thrust, but if we get hit by this obstacle, we get knocked up to 100, and we can't thrust past that because that's a hard limit, but we can thrust in the other direction, and then we get limited to 50 again. So yeah, that's all I wanted to show you for now. I hope you can use this tool to make your games awesome without having to think about a bunch of horrible vector math. And BetterPhysics can do the horrible vector math for you. So thank you for watching this, and happy coding, everybody.